So, my name is Deven Corzine. I live in Cincinnati, Ohio. I've been programming Perl for over 33 years and regular expressions for over 35 years. I've attended every YAP, CNA, Perl conference, whatever, since 2006, plus one in 2002. This is my second time as a speaker. It's an updated version of the talk I gave in 2018. What could possibly go wrong? So there are some interesting Perl regular expression features, like you can embed a comment, do zero width, look ahead, look behind assertions, name captures, embedded Perl code if you're crazy, conditional expression, define sub-expressions. I'm not here to talk about these things. So what is this about? How to work with large, complex regular expressions without getting overwhelmed by the complexity, capturing versus non-capturing groups, how to get numbered captures right every time, greedy versus non-greedy matching and why it matters, understanding the different uses of question marks, and then obligatory XKCD comic here. So if you're having Perl problems, I feel bad for you, son. I've got 99 problems, so I use regular expressions, now I have 100 problems. So here's an example of a complex regular expression. This is a real-world regular expression that was actually used in production code, and we will revisit this later. That was easy to read, right? This is fine. Okay, so quick review of some basics. A regular expression, also known as a regex or regex, is a pattern which is used to determine if the target string matches the characteristics that the regex describes. Certain punctuation characters are meta characters, which have special meaning. All other characters are literal characters, each of which only matches itself, but letters match both cases with the /I flag, which stands for case insensitive. Symbols escaped with a backslash are always literals, for Perl anyway. Not true on all regular expression packages. Letters and numbers, which are normally literals, often have special meaning instead when escaped with a backslash. The most basic meta character is a dot, which normally matches any single character except a new line. The /S flag will make the dot match a new line also. The caret and $ meta characters are anchors, which match at the start or the end of a string or line with some caveats. They don't match any characters, just that empty space. Parentheses are used for grouping sub-expressions into a single item. These groups also capture the matched text. A vertical bar is a meta character which is used between sub-expressions for what's called alternation, where each sub-expression will be tried in left to right order until a match is found. So Perl has the m/regex operator to perform a match against a target and the s/regex/replacement operator to do a substitution. Although you'll normally see that the m is not usually in real code unless you have to, because if you're using / as the default delimiter, you don't need the m. The binding operator, which is the equal tilde, can specify the target you're matching against. Otherwise, the implicit $_ variable is the default match target. And the while loop, for, grep, map, they all set that variable implicitly. It exists for a reason. Please use it. So quantifiers in regular expressions. Certain meta characters specify quantifiers, which match repetitions of the previous item in the regular expression. Since groups are considered a single item, they can be used with quantifiers for repetitions of complex sub-expressions. If the previous item is a literal, such as a letter, the quantifier only matches repetitions of that single letter, not an entire word. Matching repetitions of a full literal word requires the word to be in a group, i.e. inside parentheses, then followed by the quantifier. And regular expressions cannot start with a quantifier. Since they apply to the previous thing, there's nothing to apply to in that case. The most basic quantifier is the star, which matches 0 or more of the previous item, which means it can also match the empty string. A very similar quantifier is the plus, which matches 1 or more of the previous item, so it cannot match the empty string. The other single character quantifier is the question mark, which matches exactly 0 or 1 of the previous item, making it optional. The question mark is a meta character which is also used for other purposes depending on the context. This does tend to cause a lot of confusion. Braces are meta characters used to delimit a general quantifier. The single number form with the just n there is a quantifier which matches exactly n repetitions of the previous item, no more, no less. And note that putting 0 can only match the empty string, which is kind of pointless. And putting 1 as the quantifier has no effect because it's, saying to match one of the thing, which is already the default anyway. You can also do comma n, which is a form of the quantifier which matches no more than n repetitions of the previous item or the empty string. N comma form is a quantifier which matches n or more repetitions of the previous item. And you can see that the 0 comma form is equivalent to the star quantifier, and the 1 comma form is equivalent to the plus quantifier. The star and plus are just a lot easier to type. And then there's the n comma m form, where it gives 2 numbers, which is a quantifier which matches at least n, but no more than m repetitions of the previous item. And the question mark operator is an example of that case where it goes 0 to 1 count. So for capture numbering, what you want to do is count the opening parentheses. So with a complex regular expression, it can be daunting to identify which group goes with each capture variable. Nested groups and groups within alternations make this appear to be much more difficult than it actually is. The key is to always count the opening parentheses and just ignore the closing parentheses entirely. Paying attention to both is an easy way to get confused. But note, there is a special branch alternation syntax with the open paren question mark vertical bar. That syntax will reset the capture numbering for each alternation branch back to where it started. So if the first one was $1, the second one would also be $1 if it matches, and third and fourth, whatever. Which is a convenient thing. And there is another caveat to this, that non-capturing groups don't count. So when you have simple parentheses around a regular expression, it creates a normal group, which is actually used for 2 distinct unrelated purposes. As a syntax, the purpose is to constrain alternations to operate inside the parentheses only, and to group items and sub-expressions together as a single item, which can then be used with a quantifier. A normal group also just happens to capture the match text. Non-capturing groups, which is the open paren question mark colon followed by the regular expression, can be used when you want the syntax benefits of a group, i.e. to group things together as an item with quantifier and to constrain the alternations and whatnot. So if you want to get the syntax benefits, but you don't actually want to capture the match text from that group, that's when you want to use the non-capturing group. But when you're counting parentheses to determine which one is $1, $2, you just ignore the non-capturing groups entirely. So you want to count all the opening parentheses unless they're a non-capturing group like this. And then there's the topic of non-greedy matching, i.e. .* question mark is your friend. Historically, regular expressions only allowed greedy matching. Greedy means that the quantifiers always try to match as much text as possible and only give it back if necessary to get a match for the overall regular expression. Perl extended the traditional regex syntax to allow quantifiers to be followed by a question mark to use what's called non-greedy matching. Non-greedy means the quantifier will try to match as little text as possible, starting with the empty string, and only match more if necessary to get a match for the overall regular expression. And then this usage of the question mark is distinct from the usage of the question mark as a quantifier itself. A question mark following an item is the normal quantifier to make that item optional. A question mark following any other qualifier, should be quantifier. Any other quantifier modifies that quantifier to use non-greedy matching. That means that a parenthesis regex here like this with 2 question marks after it is valid, and it performs an optional match because of the first question mark, and it's using non-greedy matching because of the second question mark. So this construct will match the empty string if possible and match the regex inside otherwise if it's necessary to get a match for the overall regular expression. And note that this is maybe poorly worded. Having a single count in braces like this with an n following by a question mark, adding the question mark has no effect simply because it can only match the number you gave it. So it's kind of pointless, just like adding a 1 is. So here's an example. So suppose you have an XML file with these tags in it. You could try to use this regex to extract the first names. So you match person, first equals a quote, followed by some string, followed by another quote, and angle brackets. So this regex correctly returns Larry for the first example, but the second example returns this, Larry last equals Wall, because it's greedy. This is because the dot star is greedy, matching as much as possible. And because it's possible to match all that stuff in the middle before it gets to another quote, it will do it. So one way you can try to fix that is you can restrict the capture to only capture characters that are not quotes. So this matches all the first names correctly, so that's great. But let's try the same thing with last names. Works fine for Wall here. But we're only getting O instead of O'Reilly because it finds another quote there. It's not the same matching quote, but it's not trying to figure that out in this regular expression. So, not good. We can use an alternation in a non-capturing group to capture the single and double quotes independently. And this actually does work. But it's not quite as convenient since either $1 or $2 could be set depending on which matches. So, But you can fix that too if you use that branch reset feature I mentioned, which works correctly and will always use $1 for the match here because it resets that second branch to be the same counter. However, if you're stuck with Perl 5.8, the $1 or $2 is the best you can do because that was introduced in 5.10. Or you can just use non-greedy matching, which is much easier. So instead of that, so here, this example is actually matching the quote itself so that the \1 will match the same quote for closing it. And then the $?? will match as much as it needs to, but as little as possible to try to get the text that's in between. You could also get away with, the problem is if you were to try to use this with the both quotes on both sides, it would go back to matching just O because you really need to make sure that you're using the same opening and closing quotes for this O'Reilly example here. So the $?? Is the most common and generally handy non-greedy matching idiom, which will match whatever, but only enough to allow the overall regular expression to match successfully. So, understanding complex regular expressions. The key to understanding complex regular expressions is the insight that all complex regular expressions are composed of simpler ones. It's turtles all the way down. To create a complex regular expression, start with the simpler regular expressions that match part of what you want, combine them together to describe more complex patterns. To read a complex regular expression, break it down into the simpler regular expressions that it was built from, and identify how those were combined to describe the whole. And you can use these techniques recursively for the more complex ones. So, you remember that example from the start? We can use that to practice it. I did not finish all these slides, but I've got a few of them. So here's the example. So this regular expression is using braces to delimit the regular expression instead of the default / delimiters. Therefore, the M operator is required to do a match. Usually it would be omitted if you're using the / delimiters. The reason I chose to put the braces is so that these regular / characters, because the braces are used as a delimiter, those slashes inside the regular expression are just regular characters now, and they match literal slashes, but they don't need to be escaped. If you're using a slash as a delimiter, you would have to escape them with a \. And so this regular expression, at the outermost part, it's anchored with the start and end of the string. And then after the anchor, the regular expression starts with a non-backtracking group, which was not something described earlier, but it will cause the match to fail rather than backtracking into this group to try to match the full regular expression, because it would never succeed in this example. So this is for efficiency. It's not really needed to make it work. It would just potentially waste more time in a failure case. But inside that non-backtracking group, there is a normal capturing group, which will capture the matching text to $1. The capturing group contains a slash, which matches a literal slash character, as mentioned before, followed by a question mark, which is, as you recall, a quantifier, which makes that slash character optional. So I didn't get to do I was going to do, a walkthrough of the rest of this, but I ran out of time to make the slides. But that's the general technique. And then people might ask about this /x flag. It's often recommended, and in this case, it's a good place to use it. So this is what that same regular expression looks like, using the /x to break it down and with comments on the entire thing. So you can see what each line here is doing, basically. I didn't comment the anchors themselves, but everything else is commented here. And it's showing the assignments into variable names to see what those actually are doing. In this particular example, it was matching a file name, getting back a leading slash if there was one, and then the remainder of a directory name, which is what that .star was. And then the directory path is optional, so there's a question mark after that non-backtracking group. And then the next group captures the base name of what was actually a feed file name. And the first part was a prefix that could be on the feed. And then there was these terms, nightly or reprocessed, that could be in there to tag it as certain types. There was a site code that could be present there that it needs to find and utilize. Then it matches a timestamp, which is at \D8 and D6 is the date and time, basically, in ISO form. And then it allows for additional information arbitrarily to be after an underscore. And then it has to end with like a .csv extension. And there could be a processing timestamp, which is another 14 digits here. There could be another .csv or .stats extension after that. And it could be compressed, so it could have a .gz or .bz2 extension after all that. So that's what that crazy regular expression actually matched. And like I said, this was used for production code. So, questions?
True.
Yep.
You have that appears to allow you to have a file that have .csv followed by another .csv.
Yep, it does. That was because of the nature of the particular files in question. They actually did have that sometimes. Yeah. It was because they would come from source files that then got processed and suffixes added, and that's how that happened. But yeah, that's not accidental, but it is odd. I agree. Any other questions? Guess everybody's overwhelmed.
I think that was an excellent talk.
Thank you. So I guess we're done. All right, thanks.